This is the first of a video series where I will make my own ray tracer. Working on rendering and simulation is just a dream for my career, so I'm making this series thinking there's no sense waiting. I'm hoping along the way I'll get advice from people who know more and be a resource to people who know less. My goal for this project is to make a short film and render it with my own code. Suffice to say, this will not be easy, but the first step is getting started. While I create this solution, let's talk about the tools being used for this project. I'm going to simultaneously write this in two different ways. Once with ComputeSharp, which is a very cool library that's going to convert some C# into an HLSL shader that can run on my GPU. We're also going to write it with just DirectX and custom HLSLs. While this will initially be harder, it is also better designed for this goal. More best practice is designed for DirectX, and as a relatively small library, ComputeSharp is likely missing features that we'll need. Part of my goal is to identify those features for ComputeSharp and inform the developer. Now that the basic project layout is done, let's talk about the components that we'll need. First, we have a camera. The camera sits at an origin, where the rays will come from. Then our camera has a target. This is a point the camera looks at. This is a convenient way of representing the direction of the camera, but it doesn't allow camera rolling rotation, so we might change it later. Next, it has a field of view. This is the distance from the projected view to the camera origin. This is also known as the lens angle. We'll talk more about this when we begin casting rays. Here's an animation of a ray being cast from the camera and bouncing off an object. In this example, the ray strikes the target, but that doesn't necessarily happen. Now to put this in code. This code defines a class containing two vectors in R3, one for the camera origin, one for the camera target. It also has a number to track the field of view. As simple as this code is, it can't run on the GPU because the class is a reference type. We need to rewrite it as a struct to run in ComputeSharp. We'll start by creating a new project for our explicitly ray tracing code. As I rewrite the camera, you may notice that I wrote a static method called create instead of a constructor. This is because ComputeSharp doesn't handle constructors. Put in some comments and we're done with this struct. We're not quite done creating cameras yet, but before we finish, let's talk about how rays are created. For each pixel, a camera will emit a single ray per sample. For now, we're only doing a single sample rendering, so one ray per pixel. Let's take a look at rendering a 3x2 image with this camera. Before creating our ray, we need to derive some more camera specs that will make this easier. First of all, we're going to find the viewport height, then the viewport width using the aspect ratio. The aspect ratio is our image width divided by image height, in this case, 3 divided by 2. The viewport height, as if the field of view were 90 degrees, is our basis for scale. The center of the image, the top of the image, makes 1. We're going top to bottom though, so we'll make the height 2. Then to account for the field of view, we'll multiply that by the tangent of the field of view divided by 2. Just to confirm, 90 divided by 2 makes 45. Tangent to 45 makes 1, so that checks out. To find the viewport width, multiply the viewport height by the aspect ratio. Now let's find the camera direction. The direction is the origin minus the target. Since our origin is 0, this is just negative the target. We'll also normalize our direction, which means we'll calculate the vector with an equivalent direction and a magnitude, also known as length, of 1. We'll call this W. Next, we'll define up in global space as the y-axis. Because this is assumed and not a parameter, the camera can't roll, but that's fine for now. Then we can take the cross product of the y-axis and w to get the horizontal tangent vector. We'll call this u. The cross product of w and u will give us the vertical tangent vector, v. Before we continue, let's isolate u, v, and w to compare them to x, y, and z. The target is at a 10-degree angle below the horizon. As a result, u, v, and w are their own local coordinate system for the camera, 10 degrees off from the global xyz system. Now let's continue. If we multiply u by the viewport width, we get a vector representation of the camera width. We'll call this the horizontal component. V and the viewport height make the vertical component. Finally, we can find the position of the bottom left corner by taking the origin and subtracting w, half the vertical component, and half the horizontal component. Now we can finally create rays. Rays will have an origin and a direction. Each ray will be generated based on the fraction of the image they cover as a float from 0 to 1. The bottom left corner is 0, 0. The center is half, half, and the top right corner is 1, 1. These positions are called u for the horizontal fraction and v for the vertical fraction. The origin of the ray is the camera origin. The direction of the ray is the bottom left corner plus u times the horizontal component plus v times the vertical component minus the camera origin. Here the rays created would be at 1/6 and 1/4, half and 1/4, 5/6 and 1/4, 1/6 and 3/4, half and 3/4, 5/6 and 3/4. Now let's program this. First, we'll create array class containing an origin and direction. Again, you'll notice the create methods in place of constructors. This time I'll also point out the public fields in place of properties, as you would usually use in C#. This is again more ComputeSharp limitations. The full camera is separate from the camera because we will make the full camera on the GPU using the raw camera. So we still need a GPU accessible version of the raw camera. The full camera also has the additional context of the aspect ratio, which the raw camera is independent of. In the full camera create method, we calculate the bottom left corner and the horizontal and vertical components to store on the object. We'll also make a method that creates arrays. This method takes the U and V pixel positions and has the camera create an array for that position. Since ComputeSharp can't handle instance methods, we'll have this method take a full camera as its first argument. We'll even call that argument @this. Cheeky. Now that we're creating arrays, let's make our first thing for them to collide with, the sky. When an array doesn't hit any objects in the scene, it hits the sky. Collision with the sky behaves as if the sky were infinitely far away. As a result, ray origin becomes entirely irrelevant and we can find the collision point exclusively with the ray direction. In the future, we'll allow far more options for the sky, but for now we're going to create a linear gradient from -1y to +1y, where -1y is a specified color we'll call the albedo, and +1y is white. Now we'll quickly create a sky class containing the albedo, and again for the GPU. But wait, why are we using a vector 4 for the color? I'll explain. This is an RGB cube. It is a representation of color between 3 dimensions. This shows 3 of 4 channels we will use for color: red, green, and blue, the primary colors of additive color space. These make up 3 of the 8 corners of the cube. 3 more are yellow, magenta, and cyan, the secondary colors of the additive color space. Finally, we have black for no color and white for all colors. A 4th channel is opacity. These 4 channels are the components of our vector 4. Now that we understand how color is represented, our sky can return a color based on an array that fits it. After we normalize our direction, we're left with the range -1 to 1, but we need 0 to 1. Therefore, we add 1 and multiply by 0.5. This maps the range linearly to 0 through 1. Then we take the position and multiply it by the albedo, and add the inverse of the position times white to get our color. This will make a gradient based on the y direction of the ray. We're going to very quickly create the eye renderer. This will be massively expanded on in the future, but for now it'll be very simple. It can be told to render, and it takes a buffer to render to. This abstraction is important in case we want to use the same render viewer for a preview or rasterized scene as well as our ray trace scene. Now we'll quickly create our scene object. This just holds our camera and sky. In our path tracer, for now we'll quickly cast a ray for each pixel, then hit the sky. This is where we really see ComputeSharp in action, so I'll explain how it works in greater detail than usual. The auto constructor attribute is provided by ComputeSharp and will create a constructor for the shader with all the fields. It's just convenient. The struct implements iComputeShader, which specifies to ComputeSharp to compile it to an HLSL compute shader. As an HLSL, the execute method will run in parallel. Using the thread IDs, you can grab the position of an execute instance. Now we'll take their position, then cast a ray and write to the buffer accordingly. It's a little inefficient to calculate the full camera on each thread, but we'll leave it as is for now. Then we'll make the HLSL ray trace renderer, which will be an implementation of our eye renderer for ray tracing in ComputeSharp with HLSLs. For now, we'll write directly to the buffer we're provided, but this isn't wonderful practice, so we'll make some modifications later. Final step before we've got something we can show for all our work, the render viewer. The render viewer will implement the iShader runner for ComputeSharp.WinUI. This marks a wrapper for a shader to run in the Compute Shader panel. The Compute Shader panel will handle printing our pixels to a swap chain, so this just wraps our iRenderer in a class that the Compute Shader panel can use. Throw the Compute Shader panel in the XML and we're done. Almost. Finishing touches. I made a few mistakes in the code along the way, so let's fix those. First off, I forgot to mark the path trace shader as partial. Turns out naming our arguments @this does not work with HLSL, so we'll need to rename those. I forgot to bind the render viewer to the Compute Shader panel. And finally, we'll give the scene an actual camera and sky. Origin of 0, 0, -1, and target of 0, 0. The sky albedo will be 0.3 red, 0.7 green, 1 blue, and 1 alpha. All of this gives us this result. Here we have a gradient from albedo to white, exactly as discussed. Next time, we'll either start putting objects in the scene, or rewrite this with DirectX. Thanks for watching. Hopefully the quality of this video wasn't too bad. If this takes off at all, I'll go buy myself a better mic. I'm currently using the mic for my Surface headphones with RTX audio and a GTX card, so there's room for improvement. And before calling this done, I'm going to quickly give some thanks to my sources. Ray Tracing in One Weekend by Peter Shirley was a massive contribution to my understanding of this content. Currently, a lot of the code will look very similar, but that will change pretty significantly once we get more into the GPU operations. I'd also like to thank Sergio Pedri, the developer of ComputeSharp. His library is making this so much easier, and he's been wonderful at responding to my questions about it. I worked with him on various stuff in the past as well, and he's just a great guy. On that note, see you in the next video.